We recording? Yeah. So here's what happened with you guys in your exam. So what you see, first, Cheryl asked a great question. Was this exam out of 50 or 100? It's out of 50. If you want to make it out of 100, double your score. And that's what it would be out of 100, if you want to think of it that way. But a more accurate way of thinking about it is, when you get your out-of-class part back, you can add that to this, and that's what your actual out of 100 will actually literally be. Now, I just did some analysis of my 243 class. Their out-of-class and their in-class were essentially identical. So however a student basically did in one, they basically replicated that in the other. That does not mean you guys will. If you didn't do as well as you hoped on this, maybe you kicked total butt on this. I mean, it's possible. It's possible. But this is what happened so far. This looks far worse than it actually is. The average, that's what mu is up there. The average is 27. The average is 27.
Oh, wow.
The reason that's so low is because there's at least, that I can remember, 5 zeros in there. Legitimate zeros. People that couldn't make the exam because of sickness, because of other plans they hadn't made up. There were also at least, I believe, 3 or 4 zeros that people just didn't show up for the exam at all. I haven't heard from these people in 3 weeks. So that's a little bit of an artificially low number. There's another number that I like. You can see, look, mode, 0. The mode is the most frequently occurring test score. That means of all the test scores that there are out there, the one that showed up the most was 0. That's ridiculous in a class of 43 people to have most zeros. And that's, I say ridiculous, it's because it's ridiculous statistically. It's never happened to me in 20 years of doing this job. And it's because of a number of factors. Like I said, a bunch of folks couldn't be here for legitimate reasons. And a bunch of folks just didn't show up for whatever reason. So, whatever. So they came up 0. So when that happens, I like to look at the median instead. The median takes out the distance of how far away things are and simply puts them in order. So, in other words, there were a whole buttload of zeros. In this graph down here, I love this graph. It's called a box and whisker. We're going to play with this in the end of 105 this term. Every place you see a transition from here to here, and then from there to there, and then from there to there, and then from there to there. There are 43 people in this class. Roughly 8 test scores fall in each of these ranges of values. So there were 8 test scores between 0 and 4. There were 8 test scores between 4 and 34. There were 8 test scores between 34 and 44, and there were 8 test scores between 44 and 50. This is like the most bipolar data set I've ever seen in my life. 25% of the class got a 44 or better, but 25% of the class got a 4 or less. And then this, half of the class got between a 4 and a 44. I don't even know what to say. It's so interesting. It's like tripolar. It's just interesting. It's very, very interesting. This sigma up here, this number, and we'll come back to this number. We're going to come back to this number in this class too. That's a measure of variation. A plus or minus. You ever seen the phrase plus or minus 4%, plus or minus 5% in the median? That's kind of what that is, plus or minus. So the average was 27, plus or minus 19. Now you think about that. 27 plus or minus essentially 20. So we're anywhere between a 7 and a 47, which is essentially what you're seeing in that box. Crazy. It's crazy results. They're all over the board. I can't explain it. I can explain some of the zeros because people told me they weren't going to be here. We're going to make that up, obviously. But it's such a, here's the graph of it. Look at where the spike is. That's the zeros. Here's everybody else. Now what's interesting is, if you take the zeros out, the remaining data actually follows the shape I was expecting. Most of the time when I give exams, the data ramps up like that from least to greatest. It's just this one started way further left than I'm used to them starting. So who knows why? But we're gonna figure this out. Oh yes, Cheryl. Yes. Hang on a second. Get a picture of it. Yeah. Very good. Very good. So I don't know why, but I will tell you this. There's a rainy day project coupon. Some of you may have used already. I'm not sure if you have or not. And that exists in case you forget to turn a project in. You can turn it in for up to 24 hours late. There are also 2 rainy day coupons for exams. Let's go find them right now so you know where they are. Okay?
Yeah, let's go find those.
Yeah.
Let's go find those.
All right, so, do you remember where the rainy day project coupon is?
Yes, kind of.
Where is it? We're going to have to go to find it. Course information. Schedule page.
right there.
Rainy day coupons. See where I'm at? First week, first day. Rainy day coupons. There's the one for the projects. Make it a little bigger. Controller shift up. Maybe it's control up. Huh? How do you make this bigger?
Move your
Control
mouse
up.
to the bottom of the screen and it'll highlight. There you go. That
Oh, cool. Well, that's like, thank you.
Oh, that's so much better.
So there's your, usually control and up does it, but whatever. Rainy day project. This guy up here, whoops, I'm highlighting. This guy is for projects. This is the guy I want to look at right now. Rainy day exam number 1. This allows you to get up to 5 points back on the in-class part of the exam you just got back. 10% of the points back. Up to. Now, if you only lost a couple, if you were one of those folks that got a 48 or a 49, you can get those 2 or 3 points back or 1 point. If you lost 15 points, you can get 5 points back. You can't get any more than 5 back. But here's what you have to do to get them. You do your corrections on a separate sheet of paper, and you attach your original exam to that. So don't change anything on the original exam. I want to look at what you did first. And we'll look at your corrections side by side. Okay? You print this coupon off too. This has to come with it as well. Then, this is the key part, and I will not give you points if you don't do this, so please do it. You have to explain in a sentence what you did wrong the first time on anything you correct, and then another sentence saying what you learned by doing it a second time outside of the exam time frame, the time crunch of the exam. And also importantly, they have to be correct. I had to add that line about 4 years ago because people were turning in stuff that was wrong. And they said, well, I wrote the sentences. And I'm like, yes, but you didn't correct anything. Well, it doesn't say that to be right. It's called corrections. It doesn't have to be right. So welcome to America and the land of lawyers. So now I have to add, the corrections must be correct to get the points. So, yeah. So make sure they're right as well. Does that make sense? So what are you going to have? You have a coupon, that exam, separate sheet of paper, couple sentences, and you can correct as many as you want. I recommend correcting everything, honestly. Because what I've had some students do in the past is suppose they missed 10 points. They may only correct 5 because they only get 5 points back, but they correct that 5 points wrong, which means they don't get any points back. So overcorrect, if you will. Correct everything you got wrong. I mean, if you missed 7 points, fix all 7. You'll get a max of 5 back, but why do I do this? Why do I do this? In what way? I love that, Cheryl. I can think of 2 ways this helps you be successful. Can you give me one of them?
Because you're going to learn the correct way to do it.
That's the main motivator for me is you're going to go back and look at your exam again, and you're going to figure out what you did wrong the first time and fix it. That's the main way. That's the main reason I do it. But the other reason, okay, go ahead.
That's what I was going to say.
Exactly. Points. You won't do this unless I give you a reason to do it. The reason to do it is I'm going to give you some points for doing it. So there you go. You get the 5 points by doing the corrections and doing everything you have to do. Plus it makes you read directions. Hopefully you'll read all this. I know it's annoying. It's like, why don't you just have a coupon that says fix the corrections? Well, because you have to have all this because that's part of it. I don't want this exam to be the end. It's not the end, it's the beginning. It's the beginning of that assessment. You're going to go back and look at it again. You're going to see how it ties in the stuff we're going to be doing today. So that's what happened on the exam. Ben, you question or just stretching? Just stretching. Be the man. Be the man. Cool? Fair?
Mm-hmm.
All right.
Very cool.
So on Wednesday, make sure you bring that. Thursday, thank you. Next class. Let's just start it. Next class, make sure you bring these corrections back with that. And then next class, I will also give you these guys, the outer class parts, so you can staple those together. And then put it all together, make it a 100-point assessment. And then the progress reports on Friday will go out, and you'll actually have all this stuff in the progress reports. And hopefully by then I didn't get stuff back from the testing center yet.
Okay, so when should I turn in my correction then? Will I?
When you get yours back, Leslie, then you can turn yours in. Yeah, and I've got about 5 exams. Remember how I said there were so many zeros? A bunch of folks legitimately weren't there that day, and when I get those back, you get them back from me, then you can do corrections in the next class. I just don't know when that's going to be. I mean, I'm hoping today. This is why I'd much rather, if it ever happens again, rather than putting stuff in testing and tutoring, we'll figure out something else to do, because it takes me forever and 5 days to get stuff back for whatever reason. I don't know why. I mean,
I took it the same day that you guys did.
and I don't know why it's not back yet. So it's between the library and Pioneer is a very long distance. It's at least 150 feet. So anyway, we'll get them back, and then when you guys get them back, you correct them in the following class. Cool? How was this? This is the outer class part.
Some parts, I was
Right? Some parts okay, some parts not. Yeah? What do you think, Janelle?
Near the end, when we did the equation,
Uh-huh.
I'm used to having us put like 0, 10, 20 in the X
Again, just turn in what you've got, my friend. Turn in what you've got. You've probably done it correctly. Just turn in what you got. Turn in what you got. So basically, the reason you have an out-of-class part and an in-class part is because, oh, thanks. You got an out-of-class and an in-class part is because the out-of-class ones generally take a little more time to get through. And I wanted to give you the full, like, 2 weeks, almost 2 weeks of time to get through some of those. They were more time-consuming. Reading those little elevation charts, time-consuming. Not the kind of thing you want on an exam. The pilot view question is straightforward, very, very straightforward. I actually did that math while I was running the computer piece with some friends weeks ago, and I'm like, okay, this is cool. If I can do this math while I'm running the Butte repeats, it's a perfect in-class assessment to do. And having the formula on the board, I think, was huge, too. This way, the out-of-class is great because you can just take all the time you need, all the resources you need. Anybody trying to ask the tutors for help on that one? Good. Don't, because they're not allowed to. Okay? Okay. Fantastic. Cool. Don't put that there. I'll forget to. All right. Let's mute this down for a second. So what I want to do today is I'm going to pass a bag around. There's a bag of pennies. Everybody take a penny and just keep passing it until everybody has one. What I want to do is continue modeling. I want to continue modeling data. But I want to maybe explore another model that we haven't explored yet. So, while you guys are passing pennies around, I'm going to put... Wait. Yeah. While you guys are passing the pennies around, all I have... Hang on. On the board, I'll put something while we've already done. And you can remind me of what makes the modeling that we've already done that type of modeling. So, the modeling that we've done so far. Your last exam consisted of linear modeling, and it consisted of quadratic modeling. And I intentionally made the decision engine fairly simple for you on the exam, because I said, here's data, find me a best fit line. Here's data, find me a best fit parameter. But if you had to make the decision yourself about what, you didn't like that, being told?
No, I like being told.
Oh, okay.
Myself.
Oh, okay, well good. I didn't want you to have to make the decision because it's not always obvious what shape the data is, and that's what I kind of want to wrestle with today in class. So, how would you decide whether between these two models, if you had to be either linearly modeling data or quadratically modeling data, what decision would you use to decide whether or not data was linear or quadratic? What would you be looking for, do you think? Say that again. In what way, Janai? In what way with exponents? I love that. Like something squared, something cubed?
Yeah.
I love that. But I'm gonna give you a chicken egg question. The only way we'd have, so basically what Janai is saying correctly, by the way, is linear is going to be of this form, y equals mx plus b, or a, let's go ax plus b, I like that better. That's going to be a linear model, so both the exponents are to the first power, okay? And quadratic is going to be y equals ax squared plus bx plus c. So you got a second power term. And that's fantastically correct. The problem is, if all you've got is data that's in front of you, how do you know whether it should be a first power or a second power model? Does that make sense, Janai?
First or second?
Go ahead, Jake.
By graph it. You can graph the data.
Tell me more.
You can graph the data, look at whether it's a straight line and it's going in like a pretty predictable angle, or if it's at a slope, at like an angle.
So I love this, because what does the predictable angle imply? I love that, Jake, by the way. Say that again.
First difference.
Is what? I love that,
It's
Kath.
consistent.
Good. What you're looking for, I'm going to draw I'll draw 3 different data sets that are all linearly related. So here's an example of maybe some linearly related data sets. Okay, that would be as x gets larger, y gets larger. And it's fairly predictable. I love the word predictable. It's predictable because as x moves over a certain amount, y moves up that certain amount. X, y, x, y. But you don't have to increase upward. You can also increase downward. So it could be something like this. Something along those lines. Where as x gets bigger, y gets smaller. But it's still consistent, right? X moves over, y moves down. Over, down. So you're still seeing that consistent slope. on average. Now, not all the data points obey it perfectly, but you're still seeing that stair step of behavior. What's my blue one? That's right, blue. Blue does the same thing. Over, up, over, up, over, up. So you get this kind of regular, like walking up and down your stairs in your house. Another linear model that's not as interesting to talk about is if it was a perfectly horizontal line. I wouldn't even bother drawing that because that's kind of boring. Go straight across. Or a perfectly vertical line, because you can't model those in your TI. They're not much fun to talk about. So yeah, so basically I heard first difference from someone that was perfect. Is that you, Amy? Back. First differences, beautiful. First differences, consistent. So you got a first difference in the y coordinates consistent. Love that. That's a way of using the data itself to check for a pattern versus the graph of the data. Because the graph, suppose the graph doesn't look as, if you will, neat and as regular as I've drawn it. The first differences of the data allow you to get, and the first two questions on your exam, I made them perfect linear and perfect quadratic. So if you check for first differences, you're like, oh, it's whatever it was, 7, 7, 7, 7. Okay, got it. So that was the point. Real data is very rarely perfect. It's perfect-ish. And that's, again, back to ish. We have to talk about what ish means. And we'll get into that today. We'll get into that today as well. How about quadratic? How about quadratic?
It's predictable.
Aha. What is predictable with quadratic?
Second.
Boom. Brandy, the second differences are now. Now, what does the data actually look like with quadratic data? Say that again.
It's a parabola.
Good. It's parabolic. Very nice.
Me. PJ, Penelope.
Penelope, PJ. There we go, Penelope. So it's predictably quadratic looking. So often it does something like this. And if you continue it, it's going to predictably do something like this. So that's if you, for example, if you threw something on Earth. If you threw something on Earth, that path it would take would look something like that. Or if you were looking at, say, my speed on my bike going down that hill, it might look something like this. Start over here actually, but we started at 0 and it would go something like this. The problem with this is the first differences are not consistent. The first differences are not consistent. If you got the same x value, you get that. Same x value, you get that. Same x value, you get that. And you're starting to see that those first differences are not consistent, but the differences in the seconds are. The second differences are consistent with quadratic. Okay. Second difference, or second delta, I guess. Nice. And in a nutshell, that's what we've been kind of playing with so far, are those kinds of models. But what I want to do, I was thinking about this, I'm still kind of in the process of designing this course, and I had a whole bunch of other types of modeling ready to go. But then I thought about how you really didn't care for the math too much in the quadratic modeling. And I said, well, I can torture with more modeling, or we can get into probability more quickly, and statistics. I thought you might like that more. So there is one kind of modeling left, though, however, that I think as humans in this world of technology and finance, we need to understand and cope with, and health and things like that. We really need to learn how to cope with. And that's why I gave you all pennies today. So what we're going to do today is I'm going to count first. 1, 2, 3, 4, 5, 6, 7, 8. Plus 6 is 14, 19, 25, 35, 37. I'm going to count that again. I'm going to count myself too. So I got 5, 10, 15, 20, 25, 30, 35, 38. Okay, there's 38 of us in here. Everybody got a penny? Are there pennies left over? Oh, here they are. Perfect. Here's what I want to do today. We're going to collect some data that involves flipping a penny, which might seem stupid, and that's okay. It probably will seem stupid at first. It's going to seem kind of frivolous. But I promise you that there is an application to this. That actually, it turns out it just happened to pop up. I just got news of this Amanda Knox case. I'm totally out of the loop, just so you know. I'm too busy raising 5-year-olds and giving lectures at freaking conferences. Was that a long time ago? I'm just getting news of this now, but apparently it just was back in the courts relatively recently. Coin flipping was actually part of the decision that was made. And there's a reason for that. There's a reason. Coin flipping is purely binary. And very often what you'll do is you'll test a result as if it was being compared to a coin flip. Because a coin flip has exactly 50% chance heads, 50% chance tails. And very often we can look at that kind of a thing and see if something is being effective or ineffective by comparing it to pure random chance. So we'll start that study today. So what I want to do is we're going to collect some data, and we're going to need more board than this, I think. Yeah, we'll start on this board over here. What we're going to do is I'm not going to record this entire thing until we're done. I want to set up a little t-table, okay, where x is the number of flips, and y is going to be equal to the number of heads remaining. Let me explain that a little better. What we're going to do is we're all going to start, that's why I wanted to count, we're all going to start with, 0. We're all going to start as if, we're all going to start with 38. Then we're all going to flip, and we're going to flip sequentially until we get tails, and then we're going to stop flipping. So does that make sense? So right now, there's 38 of us before we even start flipping.
What's the last word up there?
Remaining,
Remaining.
right?
Sorry.
That's actually not that clear. You fix that, Maddie. Remaining. So in other words, I don't know if that's much better. Remaining. So, everybody, if you will, take your coin, flip right now, mark what you got. We just each flipped one time. How many of you got heads on that flip? Let's see hands. If you got heads on that flip. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17. Okay. I didn't get one. I got tails. Those 17, what's up, John?
So does it matter if we start with heads? Or
Does not matter, because basically inertia's kicking up. I read a paper once. This is so cute. This is why you have to read so carefully. I read a paper once that said if you use a perfect coin flipper, people actually build these things, and you place the coin heads on the coin flipper, and it flips exactly perfectly the same way each time, you're more likely to get heads with this certain flipper than with other flipper. And I had a student come to class about 1.5 years ago saying, see, proved it to you. I was like, did you read the paper all the way to the end like I did? They said, no. And the last sentence of the paper said, but when a human being flips a coin, it's not perfect. So essentially, you can't disprove that it's 50-50. This is why it's so important to read all the way to the end of things to see. The thing says, flipper shows coins are biased. The last sentence shows that we don't have flippers for thumbs. So, you ready? U17. If you got tails, you're done for the time being. So just sit back and relax. U17, flip again. Here's the second. Here's the second. Hands up if you got heads that time. Hands up if you got heads that time. This was just the people that got heads the first time, right? Just the people that got heads the first time. If you got tails the first time, you're done flipping. So you guys that are raising your hands, you got heads the first time, right?
Yes.
Okay, good. 1, 2. You did 2? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, beautiful. You guys, U9, that got heads that time. Everybody else sit tight. You guys, U9, flip again. Flip again. Okay. How many heads did we get that time? How many heads? We got 2. 2. U2, flip again. U2, flip again. Heads. 1. Okay. My friend with the 1. This is, wait, tell me your name.
Carissa.
Krista, thank you. Flip again, my friend.
Tails.
Tails that time. Okay, so we're done. Now we're done the experiment. What we're going to do is, we're going to do this a number of times and collect data for a bunch. So that was like our first trial, if you will. We're going to create some more columns and get more of these. We may have to extend this out as we go. I'm going to turn the camera off too, because it's going to get boring really fast.